Now that we've learnt most of our differentiation skills, we can now start applying them to different types of questions. Questions that often come up require you to have knowledge about the features of graphs. So what I've drawn is a quartic, x power 4 in blue, and what I'm going to do first is draw its gradient function and then draw its gradient's gradient function, or the second derivative. In order to do that, we need to know what its gradient is doing at each point. Now I'm not going to be too accurate about this, it's just going to be a sketch, but I see that the gradient here is negative, then 0, then positive, then 0, then negative, then 0, and then positive again. The gradient is 0 whenever the tangent have a gradient 0, so like that, there, and there. Often this occurs at a point called a turning point, where the gradient changes from being positive to negative or negative to positive. Once I've got that, I'm going to sketch the points where the gradient is 0 on my dy dx graph. So I'm going to translate these points down here, down there, and the last one down here. So those will now be the new x-intercepts of my gradient graph, because that's when the gradient is 0. Now I'm looking for what is the gradient doing. Well, on the left side it's negative, and as it comes further and further towards this first gradient being 0 point, it's getting less and less negative. That's like the gradient starting down here and then coming up to there. Then the gradient becomes positive, but then it goes back to 0, so that must look like that. Then the gradient becomes negative again, but then comes back to 0 after that, so it goes negative and then must turn around, and then it's positive again, so it goes up like that. So we get a cubic, which is expected because when you differentiate in x to the power 4, you do end up with x to the power 3. We're now going to do this again for the gradient graph to give us the graph of the second derivative. Identify what the gradient's doing, so it's positive until here when we get 0, then negative, 0, then positive again. We're going to draw down where the gradient is 0. That's there. And here. Then we'll sketch in the graph based on what the gradient's doing. So on the left hand side it's positive, and it's becoming, while it's still positive, the gradient is becoming less positive as it slopes to 0. So that looks like that. Then it's negative, but it comes back to 0, so it must curve around. And then it's positive again, so it comes back up like that. And we get a quadratic, which is again expected as a cubic x to the power 3 will differentiate to a quadratic x to the power 2. Now that we have these, we can identify some important points and meanings of certain values. So we'll start at the basic graph. You should already know that when y equals 0, that gives the x-intercept. And when x equals 0, that gives the y-intercept. Looking at the differentiated graph, when dy dx equals 0, that gives you the 3, so that's these points here. In this case, the 3 turning points, which are also called stationary points. Stationary meaning the gradient is 0. When dy dx is greater than 0, which is when this graph is above the x, which is when the dy dx graph is above the x-axis, well, that's when the graph is said to be increasing, because we are increasing increasing. So we're going to use the word increasing. And when the first derivative dy dx is less than 0, well, that's when it's going downhill, so that's when it is decreasing. And that is in these points here. We're decreasing here, which is represented by being below the x-axis. Going one step further, the second derivative is new to us. When you have the second derivative being 0, which occurs here and here, if we draw that all the way up, we're looking at about that point there and approximately that point there. Now that is called a point of inflection. A point of inflection occurs when something called the concavity changes. Now what concavity is if we look at the very original graph, concavity describes sort of when does it look like a smiley face and when does it look like a frowny face. So before this point of inflection, on the left hand side, it looks like a smiley face here, up until that point there. So that would be a positive concavity. Then it goes and looks like a sad face there, so that would be a negative concavity. And then we look like a happy face here again, so we've got a positive concavity one more time. Looking at the second derivative graph, on the left hand side of this first point of inflection, so that side there, which is here, our second derivative is greater than 0. And again, the second point of inflection on the right hand side, when the concavity is positive, again we have it being greater than 0. And when the concavity is negative, which is between our point of inflections in this question, the second derivative is less than 0. So we're going to say d squared y over dx squared is greater than 0 when you have positive concavity, which is sometimes called concave up, and when the second derivative is less than 0, you have negative concavity. Which is sometimes called concave down. Now these sketches also allow us to determine what's called a nature of a stationary point. Now in some questions you'll be asked to find the stationary points or the turning points, same thing, they both mean the first derivative is 0, and to describe the nature of it. So if we look at the three stationary points, we have 1, 2, and 3. The first one is a minimum because it's going down. If you take that all the way down, the minimum occurs firstly when the first derivative is 0, and if we keep going down, we have a positive concavity. So when you have the first derivative equals 0 and the second derivative is greater than 0, that gives a minimum. Now that's the same for the third stationary point, which is also a minimum, because if we go down, we get 0 and then positive. Now for the second stationary point, which is called a maximum, because it goes up, it looks like a hill, we go down. Again, we have the first derivative being 0, but now if we keep going down, we have the second derivative being negative. So when you have the first derivative equals 0, and the second derivative is less than 0, that gives you a maximum. Now you can also determine the nature of roots by looking at just the first derivative. Because on this side here, if we just get rid of all of the gradients, Well, on this side, at our stationary point, which is again here, on the left-hand side, the gradient is negative, and on the right-hand side, the gradient is positive. That gives a minimum, and at our maximum, this point here, on the left-hand side of it, we have the gradient being positive, and on the right-hand side, we have the gradient being negative. That gives a maximum. So if I draw that out, you also get a minimum when your gradient at the stationary point is 0, and before it is negative, and after it is positive. That gives a min. And a max, when your gradient is 0, before it you have a positive gradient, and after you have a negative gradient. We're going to look at examples and use both of these methods to find the nature of the root. So, say you are asked for the graph y equals x minus ln x, where you're also told x is greater than 0. Find turning points and determine their nature. So turning points means dy dx equals 0. So we're going to differentiate. 1 minus, and ln differentiates to 1 over x. And then we're going to make dy dx equals 0 for the turning point and solve. Well, we can add the 1 over x to the left-hand side, and then times by x to get x equals 1. So now when it says turning points, it means a coordinate, so we also need the y value. So we're going to sub 1 into our equation, 1 minus ln 1. And ln 1 is 0, so you just get 1. So the point is 1, 1. Now to determine its nature, we're going to look at both options. Option 1 is to find the second derivative. So we're going to go back to dy dx, and we're going to differentiate. Well, to differentiate 1 over x, we firstly need to write this as x to the power negative 1. Then the second derivative, 1 differentiates to 0, and negative x to the power negative 1, we bring the power in front, we just get a positive, and we reduce the power by 1. We get 1 over x to the power 2. We'll substitute x equals 1, which is the turning point. So at x equals 1, the second derivative equals 1 over 1 squared, which is just 1. Now since that is greater than 0, that means we have a minimum. So we can say that the point 1, 1 is a minimum. We can also work out the nature of this by, instead of doing the second derivative, we can just go from the first derivative and create a number line where we have x equals 1 there, and I'm going to put two numbers on either side. So 2, now we are told that x must be greater than 0, so we can't use 0, so maybe I'll use 0.5, and I'm going to calculate dy dx. Well, when x is 1, we know it's 0. When x is 2, we have 1 minus a half, which is a half. And when x is 0.5, we have 1 minus 1 over 0.5, which is 1 minus 2, or negative 1. In terms of what that means as a gradient, well, we have a negative gradient, which is downhill, 0 gradient, flat, positive gradient, uphill. That looks like a minimum, so we can also justify it as a minimum. Next question. Y equals x squared times e to the power of x. And the question is, when is y decreasing? So, when is y decreasing? Well, that's when the second derivative is less than 0, which means we have to differentiate and make that less than 0. So, product rule. U is x squared, so u dash is 2x. V is e to the power of x, and so v dash is also e to the power of x. And so we can give dy dx as u dash times v, 2x e to the power of x plus u times v dash, x squared times e to the power of x. And we want to know, when is that decreasing? So when is that less than 0? In order to solve an inequality that is more complicated than just a linear one, we have to first find when it's equal to 0. So 2x e to the power of x plus x squared e to the power of x is equal to 0. In order to solve this, I need to factor e to the power of x out, leaving us with 2x plus x squared. And then I'm going to make each part of this equal to 0. So either e to the power of x equals 0, or 2x plus x squared equals 0. Now, the function e to the power of x is an exponential, which means it has an asymptote at y equals 0. What that means is it's not possible to equal 0. So that doesn't work. Our next one, this is a quadratic. Factor x out and solve. That means x equals 0 or x equals -2. So, when is it decreasing? Well, let's use that number line again and see when is the gradient negative. So number line, put our two stationary points, 0 and -2, making sure we are going the way a number line should go. That gives dy dx as 0 for both of those. And I'm going to choose a point on either side and in the middle to work out its gradient. So maybe -1, 1, and -3. So I'm going to substitute into our dy dx equation. So here. Now you can pick any of these equations as long as you haven't done anything like dividing. So because all of these 4 dy dx equations have just been factorized and rearranged and nothing's been divided, I'm just going to pick the bottom one to sub into because it's the simplest, but you can also choose the first one if you would rather do that. So when x equals 1, we have e to the power of 1 times two times 1, which is just 2, plus 1 squared, which is 3, so we have 3e. Now I don't really care what that number is, all I care about is that that is a positive number. So at least here we have a positive gradient, beside it we have a flat gradient, or 0. Then we'll substitute -1 in. I have e to the power of -1 times by 2 times -1 is -2, plus -1 squared is +1. Now again, I don't really care what that is. That gives me e to the power of -1, which is 1 over e, times by -1. So -1 over e, which is a negative number. So that is like a decreasing gradient. So like that. Then at x equals -3, we have e to the power of -3 times by 2 times -3 is -6, plus -3 squared is 9, which gives us 3 over e to the power 3, which is a positive number. So flat gradient there, positive gradient there. So what do we have? When is y decreasing? Y is decreasing when, that's this region here, x is between 0 and -2. If you're asked to classify the stationary points, well, hey look, they're here. When x is -2, we get this shape. That's a max. When x is 0, we get this shape. That's a min. So this number line method helps you find out when is a number increasing or decreasing a lot easier than doing any other algebraic method. Next question. Find the x values of the point of inflection of function of x equals 3x squared times ln x. So point of inflection that says a second derivative is equal to 0. Now we have a product rule here again. So u equals 3x squared. So u dash is 6x. And v equals ln x. So v dash is 1 over x. That means that the first derivative is equal to u dash times v, 6x times ln x, plus u times v dash, 3x squared times 1 over x. Simplifying, we get 6x ln x plus 3x. Now we need to differentiate again. We've got a product rule here again, so we need to write u equals 6x, u dash equals 6, v is ln x, v dash is 1 over x, and didn't do that. That gives us 6 ln x plus 6x times 1 over x, and then we've got to remember to differentiate this 3x, so plus 3. Simplifying, we get 6 ln x plus 6 plus 3, which is 6 ln x plus 9. As the question asks for the point of inflection, that's when the second derivative equals 0. We're going to make this equal to 0. Solving, subtract 9, divide by 6 to get negative 3 halves, and in order to solve a ln, you're going to e the other side to get x equals e to the power of negative 3 over 2. Now the reason for that is that negative 3 over 2 equals ln x, which is the same as log base e x, and the rule to change a log into an exponential is you take the base, you push the other side up with it to get you e to the power of negative 3 over 2 equals x. A couple more examples. Calculate and classify the turning points leaving your answer in exact form. Of y equals x e to the power of x. So this is a product rule question. Now this time I'm not going to write u and v, I'm just going to differentiate this on the fly. So dy dx equals, product rule says differentiate the first one, that's 1 times the second one, add the first one times the differentiation of the second one, e to the power of x differentiates to e to the power of x. So we have e to the power of x plus x e to the power of x. Turning points are when this is equal to 0. In order to solve anything with an e, we need to factorize e out. That's 1 plus x, and make both of these equal to 0. Now, e to the power of x equals 0. We've already talked about that that cannot happen. Or 1 plus x equals 0, so x equals negative 1. So we have one turning point, we need to classify it. Again, we'll look at both options, you only need to do one. One option is the number line method. Draw your number line, plot your turning point and 2 points on either side. If you can pick 0, pick 0. And we know that the dy dx at negative 1 is 0. When x equals 0, we can sub into any of these three equations because we haven't divided by anything, we've only factorized. Again, if you have done anything to that, like dividing by a negative number or something like that, you need to go back to the original equation. So I'm going to go for that bottom one because it's simplest. When x equals 0, we have e to the power 0 times 1 plus 0. E to the power 0 is 1, so 1 times 1 is 1, which is a positive gradient. That's flat. at x equals -2, we have e to the power of -2 times by 1 minus 2, which is -1 over e to the power 2, which is a negative gradient. So that looks like this here, which is a minimum. So we know that this turning point is a minimum. The other method is find the second derivative. So go back to dy dx equals e to the power of x plus x e to the power of x, and differentiate this again. E to the power of x differentiates to e to the power of x, and x e to the power of x, well, that's product rule again, but also we've already done that. The original question was x e to the power of x. So this will differentiate to the first derivative, e to the power of x plus x e to the power of x, which gives you 2 e to the power of x plus x e to the power of x, which if you want you can factorize e to the power of x out, and 2 plus x. To classify we need to sub these turning points, so x equals -1. The second derivative equals e to the power of -1 times by 2 minus 1, which is just 1 over e, and since that is greater than 0, we have a minimum. Either method is fine. Now that we know that x equals -1 is a minimum, we actually need to answer the question, which is the turning points. Now it doesn't say x value, so that implies coordinate. So when x equals -1, y equals, the function is x e to the power of x, so that's -1 times e to the power of -1, which is just -1 over e. So the answer to the question, -1 over e, is a minimum. Last example, find the x values of any turning points and of the function y equals 2x minus 4 times x plus 4 to the power of 5. Now this question doesn't actually ask for you to classify anything. This question doesn't ask for you to classify anything, so we just need to find those x values and then we are done. Product rule, u equals 2x minus 4, so u dash is 2. V is x plus 4 to the power 5. So v dash is bring the power in front, rewrite the bracket, reduce the power by 1, and times by the derivative inside the bracket, which gives you 5x plus 4 to the power 4. So dy dx equals u dash times v, 2 times x plus 4 to the power 5, plus u, now since I'm timesing u by something, I'm going to put that in brackets, times v dash 5x plus 4 to the power 4. Simplifying that up a little bit, we get 2x plus 4 to the power 5, plus 5, 2x minus 4, times x plus 4 to the power 4. And that will be equal to 0 for turning points. Now, if you were looking to expand this and then solve, that is going to take a long time. The better option is to look at what are common factors. Both our two terms, 1 and 2, have x plus 4s in them. In fact, they've all got 4 x plus 4s in them. So we can factor out x plus 4 to the power 4. That leaves in the first term the 2 and 1 x plus 4, because that was the power 5. And the second term it leaves 5, 2x minus 4, and nothing else, because the other part of that second term was the whole x plus 4 to the power 4. Simplifying, we get x plus 4 to the power 4 times 2x plus 8 plus 10x minus 20, or x plus 4 to the power 4 times 12x minus 12, and that's equal to 0. Solving both of these parts to make equal to 0, x plus 4 to the power 4 equals 0, which means that x plus 4 equals 0, and so x equals negative 4, or 12x minus 12 equals 0, so 12x equals 12, or x equals 1. Now, that is pretty much all you need to know about point inflections, maximums and minimums in the level 3 exam. But while it doesn't come up much, it is possible for there to be one other type of stationary point. And to look into this more detailed, we're going to look at the two functions y equals x to the power 3 and y equals x to the power 4. Now, if we were to differentiate x to the power 3, we get 3x to the power 2. And if you asked to find the stationary points, we'd make that equal to 0, which means x squared equals 0, which means x equals 0. If you're asked to classify that, you would then take the second derivative. That gives us 6x, and when x equals 0, that second derivative is 6 times 0 or 0. So that implies that this stationary point is actually a point of inflection. Now if we were to confirm this using the gradient method, well, number line, x equals 0, 2 points either side, say 1 and negative 1, and we'll substitute those values into our dy dx. We know at 0 the gradient is 0. At 1 we get 3 times 1 squared, which is 3. Negative 1 we get 3 times negative 1 squared, which is also 3. And so we have a positive gradient, a 0 gradient, and a positive gradient. And since that looks like that, that is a point of inflection. So we know that this one is point of inflection. Now that is correct because the graph x to the power 3 very roughly looks like that. We have a stationary point at the origin, and here we have a sad face, so that's concave down, and here we have a happy face, concave up. That is a change in concavity. Now if we look at x to the power 4, dy dx equals 4x to the power 3, so we'll ask the same question, what is the nature of the turning point? Make that equal to 0, and solve, so x cubed equals 0, so x equals 0. Find the second derivative to classify, 12x squared. When x equals 0, the second derivative is 12 times 0, which is 0. So far we have the exact same results in both of these two, and so this is sort of applying to point of inflection. But let's just check the gradient method as well. We have 0, so 2 points, 1 and negative 1. dy dx, we have 0 here. When x equals 1, dy dx equals 4 times 1 cubed, which is 4. So that is a positive gradient and the 0 gradient. When x equals negative 1, we have 4 times negative 1 cubed, which is negative 4. Now that is that. Now this here, well hold on, that looks like a minimum. When you get the first derivative equals 0 and the second derivative equals 0, you actually don't know what the point is, so you have to do a little bit more digging, in which case you have to do this gradient method. This gradient method is correct, and this tells us that it is a minimum, which makes sense because when we look at the graph of x to the power 4, we get a graph that sort of looks like this. which clearly is a minimum at the origin. So the only warning is when you have this case here, and you've found a turning point and you've shown that its second derivative is 0, you need to go back to the number line and gradient method to clarify if it's a minimum, sometimes it's a maximum, or if it's a point of inflection.